Hi everyone, today we're going to be talking about moments. Moments is a turning effect of a force. There are various effects of forces when cause objects to turn. It can change the shape and size of objects. It can change the motion of objects, so it can cause things to move or stop move if it was moving or move faster. It can also change the direction in which objects are moving. So moment is that turning effect of a force. So moment is force times the perpendicular distance at which the force acts from the pivot. Here's an equation to calculate moment. So M is moment, F is force, D is distance, and that distance is the distance from the pivot. Here we have the formula triangle for calculating moments. The symbol for moment is M. Moment is measured in Newton meter. It's Newton meter because it's the unit for force and the unit for distance together. So force is F and force is measured in newtons. And then we have distance, which is D. Distance is measured in meters. So when you multiply the unit for force and the unit for distance, we get the unit for moments. You need to remember that this distance is the distance from the pivot. So let's show you how to apply this equation. So to calculate moments, we cover moments and we have moments is equal to force times distance. If we want to determine the distance, we cover distance and we have distance is equal to moments divided by force. And if we want to find force, we cover force and we have force is equal to moment divided by distance. So here we have an example of a seesaw. So we have a force caused by the weight of the animal here. Now the force will cause the seesaw to turn, and we had said that moment is the turning effect of a force. So this 10 newtons will cause the seesaw to turn in a clockwise direction, so we call that clockwise moments, and this 10 will cause it to turn in anti-clockwise direction, so we call that the anti-clockwise moments. So there is what we call the principle of moments, and the principle of moments says that for an object to be balanced, the sum of the clockwise moments must be equal to the sum of the anti-clockwise moment. So here we have the force on the one side, so we're going to cover this side. So on the clockwise moments, we have the force and the distance from the pivot. Remember, we always use the distance from the pivot. So the force is 10 newtons. It's acting at 10 meters from the pivot. So to calculate the moments, we have moments is equal to force times distance. The force is 10. So where we have F, we'll put 10. The distance from the pivot is also 10. So the moment is 10 times 10, which is 100 Newton meters. And so the distance from the pivot is 10, force is 10. So the moment, clockwise moment, is 100 Newton meters. Now we're going to look at the anti-clockwise moment now, the anti-clockwise moment. So the anti-clockwise moment is equal to force times distance. So the moment is equal to force is 10, distance is 10. So we have 100 Newton meters. Now, based on the principle of moments, will it be balanced or will it not be? So looking at your values, the clockwise moment is 100 Newton meters and the anti-clockwise moment is also 100 Newton meters. So do you think the object will be balanced? Yes or no? Have a think about it. Pause the video and write what you think. So because the clockwise moment is 100 and the anti-clockwise moment is 100, the moments are the same, and so the seesaw is balanced. I've got a simple setup for a moment experiment. We're going to prove the principle of moments, see if it's correct. So I've got some masses here. So I'm going to be using along with, of course, I've got my pivot. Remember, the pivot is where the object turns from, and it's on a ruler so I can measure distance. And remember, it's always distance from the pivot. So I'm going to first try with a 10-gram mass. I'm going to put it at about 5 here. So it's going to become unbalanced. I'm going to try and see if it will be balanced if I put on the other side at the same distance. Good. So it's balanced. We've got 5 on one side. The distance is 5 for 10 grams and 5 on the other side for 10 grams as well. I'm going to try my 50 gram. So I'm going to take off my 5, try my 50. So I'm going to put 50 at 5 from one side. I'm going to see if it's going to balance with the 50 at 5. Good. So it's the same force and the same distance. So we can see that once the moment is the same on the clockwise and the anti-clockwise side, it is always the same. So the clockwise moment is always equal to the anti-clockwise moments. And when that is equal, the object is balanced. Now we're going to try with different masses. So I'm going to move this a little bit more to the right. And we're going to see what happens. Then we're going to try to add more to balance it. So it's going to be a little bit unbalanced. Let's see if we put 10 on this side, if it's going to be balanced. No. So it looks a little bit balanced. Good. So it's balanced now. We've got 50 on one side at a distance of 10. We have 5 on the other side. So we've got 50 at 5. We've got 10 at 10 and 10 at 15. From the demonstration, we can see that when we had 10 grams on one side at a distance of 5 from the pivot, that was equal to 10 on the other side at a distance of 5 from the pivot. And so we can see that that was equal, and so it was balanced. Now in the second case, we had on the clockwise moments, we had 50 at a distance of 10. On the anti-clockwise side, however, we had 50 at a distance of 5. We also had 10 at a distance of 10 and 10 at a distance of 15. And what we would notice is that that is also equal to 500. So we are 250 plus 100 plus 150. And so that is equal to 500, and that is also equal to 500. And so what we notice is that we could use that experiment to prove the principle of moments, because the sum of the anti-clockwise moments on one side was equal to the sum of the clockwise moments on the other side.